There are two aspects of electrical phenomena. One, associated with electricity in motion, current electricity is involved in the myriad uses of electricity in modern life. The other aspect deals with static electricity, electricity at rest. It is this latter aspect we shall now consider. I rub amber with fur and then touch the amber to two light metal-covered balls. They repel each other. I now rub glass with silk and touch the glass to two other balls. The balls again repel each other. But if I charge one ball by contact with amber and the other by contact with glass, the balls attract each other. Obviously, we have produced two kinds of effects. The effect that was produced on the amber by rubbing it with fur is called negative electrification, while that which was produced on the glass rubbed with silk is positive electrification. Evidently, unlike kinds attract each other, whereas like kinds repel. We can interpret what we have just seen by the hypothesis that all matter is composed of both positive and negative electricity in equal amounts. When the amber was rubbed with fur, the amber acquired an excess of negative electricity and the fur an excess of positive. The glass, when rubbed with silk, was left with an excess of positive and the silk with an excess of negative. On certain substances, such as glass and amber, electrical charges accumulated in this manner remain localized. These substances are called insulators. In other substances, notably the metals, negative electricity under certain circumstances moves about. These substances are called conductors. Note that the charges concentrate at the pointed end. Only an insulated metallic conductor may be charged. As soon as this insulated metallic object, which has been charged negatively, is grounded by the conducting wire, the excess negative charges pass off into the ground and are lost, nor can it be charged positively, because any positive charge conferred upon it is immediately neutralized by negative charges attracted thereto from the ground. Note that only the negative charge moves in metallic conductors. Electrical charges may be detected and their kind determined by the gold leaf electroscope. When the leaves are charged either positively or negatively by contact of a charged body with the knob, the leaves diverge because they are repelled by the identical charges on them. But even if the charged body merely approaches without touching the uncharged knob, the leaves move apart. How can this happen? Recall that electrification of one kind repels charges of the same kind. Hence, as a negative charge is brought near, negative charges in the material of the electroscope are repelled downward to the leaves, resulting in an excess of negative charge on the leaves, which causes them to diverge. When we ground the electroscope while the charged body is near, the excess negative charges through their mutual repulsion flow down to the ground. Upon breaking the ground and removing the charged body, the leaves will be found to diverge and to be positively charged. This is called charging by induction. This electroscope is positively charged. Let us use it to determine the kind of electric charge on this object. When it is brought near the knob, the leaves diverge still more. This shows that the leaves must have acquired additional positive charges by the loss of negative charges which have been drawn away from them toward the knob by the unknown charge. Therefore, the unknown charge must be positive, since negative charges have been attracted. Suppose, however, the approach of a charged body causes the leaves of the electroscope to collapse. Remember that it was positively charged. We conclude that negative charges have been forced down to the leaves, neutralizing some of their excess positive charges. Since negative repels negative, the unknown charge in this case must have been negative. In this fashion, the electroscope may not only indicate kind of electric charge, but roughly measure its quantity. However, the myriad uses of electricity in modern life involve the necessity of exact measurement. The quantitative measurement of electrical charges is made by means of this instrument called the electrometer. The principle of the electrometer is the same as that of the electroscope. The essential parts of the electrometer are these: a needle with metal knobs at the ends, suspended on a delicate fiber which resists twisting stress, and two fixed conductors near the ends of the needle. If like charges are placed upon the knobs and on the conductors, the needle is deflected because of the repulsion of identical charges. If we double the magnitude of the charges, there is a corresponding increase in their deflection. Doubling the distance between the needle and the conductor, even though the magnitude of the charges is unchanged, decreases the deflection to 1/4. This type of experiment is the basis of a law discovered by Coulomb, which says that the force between two charged bodies is directly proportional to the product of the charges, and inversely proportional to the square of the distance between them. This is called Coulomb's law. Accumulations of vast numbers of these small charges, continuously produced by static machines, can be stored in condensers, which we see here at either side. Negative charges coming from the machine into the condenser at the right repel the negative to the other condenser, where they in turn repel the negative off from the inner coating, which is left positively charged. The clouds and the earth constitute a great condenser. Before a thunderstorm, the inside of a cumulus cloud is warmer than the outside. Consequently, there is a chimney-like updraft near the center, which therefore boils over at the top. Moisture condenses into rapidly growing drops in the upper, cooler strata. These drops, falling through this updraft, become in the main charged positively, while the air and finer mist become charged negatively and are carried off to the top of the chimney. A discharge may then take place between two parts of the cloud. We are most concerned with that lightning which is discharged to earth. This may result when the upper, negatively charged part of a cloud is carried away by the wind and dissipated. Then the lower part, charged like one plate of a great condenser with positive electricity, produces induced negative electrification on nearby objects. With accumulations of a sufficiently high density of charge, we have the lightning bolt. Lightning rods afford a large measure of protection. They must, however, be so installed as to make contact with groundwater. Under these conditions, electrification quietly leaks off from the sharp points of the rods as fast as it piles up by induction from the ground. Thus we have traced phenomena of static electricity from the simple experiments with electrified amber to the appalling discharges of thunderstorms. Further study of the motions of electric charges will lead to an understanding of currents of electricity produced in great generators and providing the sinews of modern industry. They are so directed as to add immeasurably to our conveniences, to carry the sound of our voices over land and sea,